Hello everyone, I will discuss problem E, tensing and triangle of CodeTON round 5. So the problem statement says that you are given a particular line x plus y equals to k. So these points will be 0, k and k, 0. And you are given a bunch of points. Each point has some cost. So you have a bunch of points here and all the points are strictly to the left side, like in this inner isosceles triangle. They do not even lie on this line. Okay, there is no point like here. Every point is in this region only. Now you want to remove these points, and you can remove them by two types of operations. The operation of type, first I will discuss operation of type 2 and then I will discuss operation of type 1. So operation of type 2 simply means that you can pick any point xi, yi and you can remove it. Each point has a cost associated with it, ci, so the cost of this operation would be ci. And then this point will be removed. Another choice is to pick any random point here, suppose x I y I. All right, and what you will do is you will keep going up and you will keep going to the right, and uh, the this triangle, this you will basically remove all the elements which are lying in this triangle. Okay, and the cost of this is, so if the triangle has some length L, so the cost of this operation is L times A. Okay, so you want to tell that what are the minimum, like what is the minimum cost required to remove all the elements. Okay, so for example, you could maybe pick this triangle and you could also pick this point, or let's say this point, and you could pick this, you could have this triangle. So this point would be deleted, this point would deleted, and then you could delete these points separately, right? So there are multiple ways to delete them, but you want to find the minimum cost. So how do we solve it? So this problem is like good for like it has a good brute force solution as well, and then we can see the optimization for that. So first let's try to understand the type 1 operation. Okay, in the type 1 operation you are picking a point x comma y, let's say, and you are going up, you are going right, and you are creating this triangle. If you actually look at this triangle, can you tell me what these two coordinates will be? So this coordinate will be y comma k minus x, and sorry, y comma um, k minus y, and this point will be x comma k minus x. Yeah, okay. So if you look at the length of this line, it would be simply this minus this, which would be k minus y minus x, and the length of this line will also be k minus y minus x. Okay, so the length of these two lines are same. So this is a right angle isosceles triangle. Now suppose you have picked this point x comma y, and then you tell me that I will pick another point. So when I've picked this x comma y, let me divide the this segment, this portion into different regions, okay, so that we can understand it better. So these are some portions that I have divided this complete triangle into. So tell me one thing, okay, if I'm saying that it is optimal to pick this point and then delete all the elements here, then in that case, will I ever pick, like I will pick multiple I will do multiple operations of type 1, correct? So suppose this is one operation of type 1. Will I pick any x comma y, any other x 2 comma y2 for type 1 operation in this region? Well, the answer to that is no, because um, if I do this, then if I pick this element, then it will form a very big isosceles triangle which will cover this uh, triangle as well. So then there is no need to pick this x comma y because this would cover this region only. So that means if I am picking some point x comma y here, then I will definitely not perform the type 1 operation in any element here. Okay, so uh, if there are some uh, points having cost here, then we will just perform the type 2 operation on these elements. Okay, now similarly tell me about this region and this region, both will be symmetric. Okay, if I'm saying that it is optimal for the minimum cost to pick this x comma y, will I ever pick some another x2 comma y2 in this region? Well, the answer to that is no, and I will now explain the reason. So if I pick this x2 comma y2 point, okay, what will be the total cost? So the total cost will be this length. So let's call this L2 plus this length. Let's call this L1 because we have already picked this uh, triangle. So the cost for these two triangles will be L1 plus L2 into A. But instead of doing this, if I would have picked this triangle, all right, this triangle whose so this triangle will be obviously the length of this triangle will be less than L1 plus L2 because it will actually be something like L2 plus L1 and okay, so I've drawn these two triangles side by side. So this was the case when I was picking a triangle here. So we have now two triangles and this is the combined cost. Instead of that, if I took this entire black triangle, which looks like something here, so it's very obvious to see that this length, whatever this length is, it will be definitely be less than L1 plus L2 because uh, this is L2 and this is L1 and they have this overlapping region, which won't be here in this length. And this is covering actually more elements. So it is cover this bigger triangle has a lesser cost because it has a lesser length, and it is covering more elements than these two combined, this one and this one combined. So these two combined are not covering this region, but this triangle is also covering this region. So the conclusion that we actually get from this is that if we are assuming that it is optimal to pick some triangle x comma y, uh, like make an isosceles triangle at some point x comma y, then suppose this is our x comma y, then we will not do any type 1 operation in this complete region. Okay, so basically the for all the points which are lying in this region, we will simply uh, add their costs to our answer, and like we will perform the operation of type 2. Now you can see that it's very it's very beautifully, if we remove this region, okay, if we remove this region, we are now actually left with, so this is one isosceles triangle, this is another isosceles triangle, and this is another isosceles triangle. So we have actually split our problem into now similar types of structures. Like this is an isosceles triangle, this is an isosceles triangle, and this is an isosceles triangle, and then we can like independently, because this triangle doesn't affect, like the elements in this region doesn't affect the elements in this region because uh, there will be never be an overlap. So you can solve independently for this isosceles triangle, and you can also solve independently for this isosceles triangle. Okay, so based on this intuition, we will try to formulate a sort of dynamic programming solution. Okay, so what we will do is, suppose we are currently at the first element. Okay, let's assume that, so we have two choices, right? At this point, we can either um, you know make sure that this element lies in some isosceles triangle. So every element has to be deleted, right? So this first element, uh, which has some cost, can either be part of some isosceles triangle, okay? Or the other thing that we can do is we do not include it any isosceles triangle. That means uh, another whatever triangles or whatever type 2 operations we do below it, like somewhere here or somewhere here. Okay. So in that case, what will happen is all the points in this particular x position will all these points, we must do a type 1 operation on them. Like that if this is not being included in a triangle, then all the points below us will also not be included. Okay. And it's very easy to see that, because suppose I am saying that I am trying to include this point in some isosceles triangle. So um, for that, the isosceles triangle must start, like we must use this as our x comma y for performing type 2 operation, and then this would definitely contain this first element. Okay. So all these elements will be of type 1, and then what we can do is we have already dealt with this. Now what is left with us? We are basically left with a new isosceles, like new triangle, whose height is now whose length have decreased by 1. So initially the length was L, now the length is L minus 1 and L minus 1. Now here again we have like we can then recursively solve. So if there's an element here, then we have two choices. Either we contain it in some triangle, or we don't contain it in some triangle. Um, and then that would mean that all of these elements will also have to be of type 2 operations. Okay. So this case I hope is clear, that uh, suppose s- like also what in DP I am creating a DP array, something like DP of height. That means that if I have a triangle of length height, like the same sides are of length height, then in that case, what's the minimum cost to remove all the elements in this region? So okay, so basically if my height is, suppose if my side length is 6, so I have 0 1 2 3 4 and 5, then height of 0 will just look at this point uh, of, like, basically it's a sub isosceles triangle, you can say, of height 0. Height of 1 will look at this isosceles triangle of height 1, and in this region what's the minimum number of uh, operation, the minimum cost to remove all the elements. Height of 2 will look at this isosceles triangle. Okay. Height of 3 will look at this isosceles triangle of height 3, and so on. And height of 5 will mean that we are looking at the entire triangle. All right. So let's try to solve this dp. Suppose we want to find the value of dp of height. All right. That means that this was our original triangle, original big triangle of height of length k, and dp of height will mean that we are looking at this um, particular portion of the isosceles triangle. Okay, this triangle. So in this region, what's the minimum cost to remove all the elements? So here we have two choices. Choice number one is that this element, right? we do not like we can create basically at this point we can create an isosceles triangle um, uh, of some like we can do a type 2 operation to include this element, the first element of the isosceles triangle that we're talking about, or we could just not include it. So if we don't include it in any in any type 2 operation, then that would mean that all of these elements will also not be included. So uh, dp of height would be sum of all elements in so whatever this index is, suppose let's call this some x value. So sum of all elements uh, in position x plus, now what we are left with, we have already looked at these, so now we are left with a smaller triangle. So this would be plus dp of height minus 1. Okay, or the other choice is that we include it um, in some type 2 operation. So what will that mean? That will mean that from here I will, and I'm only looking at this triangle, right? I'm not concerned with whatever is before me. Okay, so from here I can pick some index j such that from I to j minus 1 I uh, create I do a type 2 operation. Okay, so the cost of this operation would be the whatever the length is, and the length, if you calculate the length, it will come out to be uh, this minus this, so it will come out to be I minus j plus 1 times a, because that's the cost of a type 2 operation. Now like I have already told you that, and we have already discussed this, that it is we cannot make any operation of type 2 in this region now, because we have made this isosceles triangle, right? And the reason we cannot make any operation of type 2 in this region is because suppose we did make an operation like this, then it would be not something optimal, because uh, what could we have done is we could have picked a bigger value, like we could have uh, picked a bigger isosceles triangle starting from the ith index, which would cover more elements and in lesser cost. So for all of these elements, I need to take their sum. I need to do a simple type 2. If I'm sorry if I'm shuffling between type 1 and type 2. So for all of these elements, I need to take the sum of their cost. So plus summation of all elements in, let's call it region R, in region R. Plus, now what is left? This triangle is left. So plus dp of j. Okay. So this is how you will, this is how your dp will look. And you can first try to just write a simple brute force for this. And for the brute force solution, what you will do is you can like in order to find the sum of all the elements, just find the index. So suppose this is the ith height based on zero based indexing, and you are going from some I to j minus 1. Then this point will be j, right? And this x-axis will be, um, since this is I, it will be k minus I, and since this is j minus 1, so this would be, I think, k minus j minus 1. So in this region, you will iterate over all the elements, and you will add their score. Okay, so that's how you will do it in a brute force manner, but how do you optimize it is the question, right? So now let's try to discuss that. All right. So this was the recurrence that we have developed, that some ith index, if you're looking at only this, like this isosceles triangle, then the cost to remove it would be the minimum of this. Okay. That means you, and there is the other operation where you just where you don't even like take a triangle, uh, and in that case you will compare this with um, dp of I minus 1. That means you will just you will not use a triangle, and then all these elements scores will be added, and whatever the score is, right? So you will at the end you can compare it with this, but uh, let's look at this case for now, which is a little more complicated. So suppose you are assuming that it's part of some triangle. So you can write this equation like this, that dp of I is equal to this region's score plus dp of j plus in this region the sum of r, basically means the sum of scores of, or sum of cost of all the elements in this region. Okay, and then we can rewrite it as I plus 1 into a plus uh, dp of j minus j into a plus r. So let's assume that we have a segment tree, or any range structure, which for each j, like we are standing at this I, right? So for each j from I minus 1 to 0, we have stored this value. Okay, so in that case we can just simply query the segment tree from the range 0 to I minus 1, because this is height 0, this is height I minus 1. So from 0 to I minus 1 we can just query the segment tree, assuming that the query segment tree stores this value. All right, now the now suppose from this ith index, we will now discuss how we actually update the segment tree, because query part is simple, but how do we update it? Okay, so first, see, j and dp of j, both of these values are known at the jth index, so they can be easily their values, whenever, suppose when we calculate even dp of I and we want to update its value, uh, we can update dp of I minus I times A in the segment tree, right? But what about this region R? This region R is actually not only dependent on J, but also on I. Okay. But let us assume that for now we have um, we have maintained this region, right? And this region contains all elements here from the this will be J plus 1. Sorry, this will be J plus 1. So it would be I minus J minus 1, and this would be I minus 1. Okay. So this region contains all the elements from these text coordinates, and the height must be from 0 to j, right? Now suppose you have calculated dp of I, and now you are going to calculate dp of I plus 1. Okay, let's assume that you are again looking at this triangle, you are creating this triangle, and you like from here to here, and like it's the same equation, you're talking about this jth index. Okay, in this case, how will this region R change for this new I plus 1 element? The For the new I plus 1 element, the triangle will look like something like this, correct? This region won't change, but the region R will have these elements added to it, right? The region R will have these elements added to it. Not only the region R, not only this J, but suppose there is some point x comma y here, which has some score, or some cost C. So for this jth index, since this new element will be add, the region will be expanded, right? For I, we have already calculated, so it doesn't matter if we expand or shrink the region. It won't. We are not looking about talking about I plus one. So this region will be expanded, and these elements are possible candidates, which like their value will be added to the segment tree at the jth index. So suppose there is an element here. So this element will affect this region, but it will also affect, suppose we are talking about this k, maybe we are talking about a triangle from some I plus 1 to k, so I plus 1 to some k plus 1, and then we would have like some other k, and in the previous iteration it had this region, but now for this point also the region will increase, right? So this C will be actually added. C will be added to the region R's, to R, for all the heights. Suppose this is suppose this is at some height uh, P1. So from all heights from, and first we are at some index I plus 1, right? So for some index I plus 1, for some height I plus 1, all the updates which are, all the elements which have basically all of these elements, right? So we will look at all of these elements which have some cost one by one, and suppose we look at this element, it has some cost, so it will update the segmentary value for all indexes from like everything above it. So if it is at height P1, so from height P1 to this ith index was the latest thing, right? So this ith index will also have this added. So from height P1 to I. So you will need to update the segment tree with this cost, but only for, only the segment tree of storing something, some this value, right? So this value will be updated for all the indexes uh, from whatever this element's height is um, to I. Okay, and so, and what I have done is I have actually stored. So since we are moving, we are actually iterating from height 0 to height k, right? Every time we increase the height, we only, when we are increasing the height by 1, we are only concerned with the, uh, suppose we are at some height I plus 1 now. So what new costs are being added here? Uh, all the all the cost associated. So this is height I plus 1. So the x coordinate will be k minus I plus 1. So all the cost associated with elements having x coordinate as k minus I plus 1, only they will be considered here, because all the other elements, since we are calculating dp of I plus 1, those other elements won't matter, and they will be used when we try to calculate for some bigger height. All right, so basically you have to have this dp, and in this dp you have this region of type, um, I think type 2 operations, and as you go from I to I plus 1, this region will expand, this region will expand, and if all the new elements which are coming in these regions, they will basically affect like whatever their height is to the uh, top index. So like all those dp values will be affected because they will include this new element in the region for type 2 operation. Okay, I will try to like give you a better visualization, hopefully. So if for this I plus 1 index I was um, going from I to I plus 1, maybe let's say, okay, and I'm creating a triangle like this. then this is the region, right, of type 2 operations. But if I do the same thing, if I'm at some I plus 2 and I'm going to some I, then the region for type 2 will increase by only these elements. And suppose there is an element here. So if suppose I'm going from this I to some um, farther place, uh, then let's say I to some k, I'm taking this triangle. Then since this region is uh, like this height is actually below this point, it won't be the part of the region. Like it won't, its contribution will not be seen in this region. So that's why only from this element's height all the way till this height, okay, like basically this minus one, all those indexes you have to update. Okay, so that's how you carry on the DP updates. I will now show you my code for this. So let's have a look. Since you are making range updates and uh, you are also making range queries, you will need to use a lazy segment tree. So I start from height 0 all the way till height k, and then for all the updates in the current x coordinate that I am at, okay, I will propagate those updates from uh, the updates height all the way till I minus 1, like whatever my index is minus 1, and whatever the updates value is. Okay, otherwise, once I have calculated my DP value, which is simply just querying, I will update the DP at my position with this value. And later on, whenever new elements are added to the region uh, for my index, they will be added in like this update only. So that's how I solved the problem. Um, Thank you for watching. Bye bye.